Okay, so this video is going through the International Edexcel GCSE paper from 2023 from January. This is the regional paper, but the regional paper has no difference to the normal non-regional paper. It's just for people who live on the other side of the world. Same content. So make sure it's the right exam board. This is obviously paper 1. Okay, so we're going to go through the paper. As I go through it, what I want you to do is pause the video, try the questions yourself. Then I'm going to talk through my sort of thinking behind the question, and then we're going to check. So I'm going to write in my answer. I'm probably going to make mistakes, but then we're going to check the mark scheme and talk through. So sort of hopefully you get the idea of how you should deal with each question. So we'll start off with question 1. So here you go. Here's question 1. We've got to identify, use these words. Pause the video, have a go at it yourself. Okay, so use the word describe. So pause the video. Now I'm going to go through it. Describe how the particles are arranged in 3 states of matter. So we can see we've got solid, liquid, and gases. We've got melting going that way, and it wants us to work out what X is, and it even tells us some different options. Really nice, easy question to get you into the paper. That's lovely. So let's write the answer. So we can see X is going from liquid to gas. So which one is liquid to gas? We'll look at those words. Liquid to gas is evaporating. And then Y is going from gas to liquid, which are those words? That's condensing. And then Z is liquid to solid is freezing. Okay, so this is just a bit of memory. You need to know these words. We'll check the mark scheme for that. Okay, describe the differences in the movement of particles in solids and gases. Okay, so the difference in movement. Well, what do solids do? Solids don't really move, they just vibrate. Okay, remember to pause the video and try this yourself. 2 marks, worth 2 marks, we need 2 points. One about solids, one about gases. So solids don't really move, they just sort of vibrate. So let's put that in. So let's bring that down here. Maybe if you're doing this paper, you probably should be highlighting parts. So let's just highlight. So we're talking about movement. Where's my highlight option? God, I don't even know. Anyway. Okay, so solids vibrate around a fixed point. Okay, so they don't move, they just vibrate around a fixed point. And what do gases do in terms of movement? Well, you're probably aware gases go really, really fast. So gases move fast randomly. So they randomly move really, really fast out of their movement. Okay, that should be 2 marks. So let's go check the mark scheme, wherever it is. Okay, so mark 1. So we can see solids vibrate around a fixed point and particles move randomly. It says allow gas particles move rapidly, quickly, freely. But I think you need to have, no, that's fine. So either rapidly or randomly, both is probably better. Yeah, so it says reject solid particles don't really move. So maybe my language was a bit wrong there. Yeah, so they are vibrating. That is movement. So I think I said they don't move; they just vibrate. But that's an incorrect statement. That vibration is movement. They vibrate around a fixed point. Okay, let's move on. So we've got question 2. This question is about gases in the atmosphere. So pause the video, have a go at these questions. Okay, so name the most abundant gas in the atmosphere. That's just a bit of recall. That's nitrogen. Okay. Name the gas that makes up 1% of the atmosphere. Okay, again, just recall. That's argon. Name a greenhouse gas in the atmosphere. Again, just recall. Actually, I wonder if you could say water. Technically, water is an answer, but what they're looking for is carbon dioxide, I'm assuming. But water is actually also a greenhouse gas. Let's see if they accept that in the mark scheme. That's interesting. Yes, they do accept water, methane. Yeah, because that is a greenhouse gas, even though. Yeah, but what they were looking for was carbon dioxide. That's what it's like. It's the one that we're pumping out as humans. Okay, anyway, let's move on. So a student uses this apparatus to determine the percentage of oxygen in a sample of air. So students often find these type of questions quite challenging. Okay, so it's all about finding out the composition of oxygen in the air. So again, I'll just zoom out so you can see the whole question. So read the question, pause it, have a go. So pause, have a go. I'll just move down so you can see the actually answers questions. Okay, now let's go for it. Let's try and get a highlighter working. It's not gonna work. Or we can just draw with this underline. Or not. God. Oh, there we go. Okay. A student uses this apparatus to determine the percentage of oxygen in a sample of air. Okay, so we've got some iron wool. Okay, well, we know iron reacts with water and oxygen. We've got a column, an upside down boiling tube or test tube, just like a boiling tube. Inside is air. We've got water here. The student's method: measure the initial length of the column of the air. Okay, so they're measuring basically how high the column of the air is. Okay. Leave the apparatus for 1 week. So after 1 week, the iron should have rusted. It should have reacted with the oxygen, with the water. There's tons of water, but there should be a limited amount of oxygen in the air. So it should have hopefully removed all of the oxygen as long as we have excess iron. Measure the final length of the column of air. Okay. All right, so we've got the initial length and the final length. So we can see the difference there. We can work out the difference, how much millimeters have been removed. State the appearance of the iron wool after 1 week. So what's iron wool going to look like after it's rusted? It's going to be rusting. So we need to know that iron, in the presence of water and oxygen, rusts. What does rust look like? So rust is a rusty or reddy, orange, brown solid. Reddy, orangey, brown solid, rusty colored. Use the students' results to show that the percentage of oxygen in the sample of air is approximately 18%. So we know that oxygen is really 21, but whenever you do these experiments, there's error, and obviously the errors come out, and it's a bit under than what it should be. But okay, so we've got to prove that their results say it's 81. Okay, so let's talk through this. So first things first, let's think about the let's think through this. So we want to work out initially what the decrease in the column was. So decrease in column was 84 minus 69. Okay, because it's decreased. Why is it decreased? Well, because oxygen has been used up from the air. So any decrease is basically the millimeters of oxygen in it. So that's going to be 11 plus 4, so it's gone down by 15. Okay. And then we need to work out how much is 15 as a percentage of the total volume to give us the percentage of oxygen. So this is, let's label this is oxygen removed. So we got 15 millimeters of oxygen removed, right? And how much the total volume of air was 84. So what's that as a percentage? What's 15 as a percentage of 84, right? So we want to work out there's 84 millimeters of air, and we want to work out as a percentage how much is 15 of 84. So we're going to go percentage of oxygen in the air, so I can't type, equals volume of oxygen removed divided by, let's use a divide sign like this, total volume. Okay, let's put the numbers in. So we've got, to the side 1 sec. There we go. Equal sign under the equal sign. Good working out, but this editor is not very nice. I'm to do it. Okay, fine, whatever. Okay, so it's going to be 15 divided by 84. And I forgot, as it is, we want it as a percentage, that will come out as a decimal, so we need to times it by 100. So times it by 100. Okay, so let's plug that into our calculator. Throw our calculator around the room. Okay, so I plugged it into my calculator and it comes out to 17.857 and a load of other stuff, but I don't need to go all the way to all the decimal places. It wants us to tell us approximately 18, so we go equals, that's 18, because you can see if you went to two significant figures, like they have, you can see that the 8 before the 7 tells us that we have to round the 7 up to an 8, so 18 to 2 SF. Okay, so that's our working. I'm assuming that the mark scheme will probably have a mark. Let's just bring this down. You get 1 mark for this, 2 marks only. Oh, and yeah, 1 mark for your final proof, I guess. 1 mark for that. Let's go check the mark scheme. Yeah, so 1 mark for basically 15, working out basically minusing the 2 to get oxygen, and then, yeah, 1 mark for your final answer. Working must be shown for mark 2. Okay, so if you didn't show your working, yeah, I mean, you should always be showing your working, but particularly on a proof question, you have to. Okay. Yeah, let's go back. Okay, now it goes on to tell us that the actual percentage of oxygen in the air is 21%. Give a reason why the percentage of air calculated from the student's result is less than 21%. Okay, so we've got just 1 mark there. There's actually a few different reasons we could put here. First sort of easy one, perhaps not all the oxygen in the air reacted. Maybe there wasn't enough iron, or maybe like, you know, it might have rusted on the surface, but not it didn't completely react, so therefore there's oxygen still left. We haven't actually removed all the oxygen. What else could we say? Maybe some oxygen could have creeped in. I mean, that's the answer they're probably going to have in the mark scheme. Let's have a look at the mark scheme, see what other answers they're going to accept. So, yeah, so main one is not, zoom in a bit. Not all oxygen in a sample of air had reacted with the iron wall. Yeah, not enough iron wall. Okay, that's what they mainly want. What else did they allow? There's water vapor in the column. I hadn't thought of that. Yeah, so if some of the water evaporates and forms into the column because of the change in temperature, that could increase, so it looks like less has been removed, and then allow, I guess, basically saying the same thing, that the reaction was incomplete, reaction too slow. Okay. Question three is about alkanes. Awesome. Organics is great. Okay. So have a read of the question. Talk about isomers. Oh no, first you've got to fill in this table. Pause the video. Okay, let's get into it. So this question is about alkanes. Alkanes, an alkane has the structural formula CH3 whatever. Give the missing information for this alkane. Okay, so we've got this thing. We can see there's 4 carbons, 10 hydrogens. So what's the name? What's the name for 4? So we know meth, eth, prop, bute. 4 is bute. So bute, it's an alkane, so it's going to end in A-N-E. Okay, so it must be called butane. And then we got structural formula, name, and then what's this formula here? C4H10. What's that? So you can see they've taken the 4 carbons and put a little 4 there. They've just, what type of formula is that? Well, that's called a molecular formula. That's a molecular formula. Molecular formula is defined as a formula where you have the exact numbers of atoms in a molecule. So it's only for molecules, only for things with covalent bonds, which is all of organics, and it's the exact number. You can see it doesn't show any structure. It shows no structure. So actually, a couple of organic molecules might have the same molecular formula, but a different structural formula. Okay, so that's a molecular formula. Empirical formula is defined as the simplest whole number ratio of elements in the compound, the simplest whole number. So what can we divide this by? What number could you divide both of those by and still have a whole number? So you can see the answer is 2. We could divide both sides by 2 and we'd still get a whole number. So therefore it's empirical formula. What's 4 divided by 2 is 2, C2. Does it allow subscript in this thing? It does not. Put it on, so I write CH. And I'll put it freehand. So it should be. It's going to let me draw. Not really. Okay. Let's do it here. So it should be C2H5. Control P, is it? Never mind. Okay, so that's the answer. C2H5. C2 is empirical formula, simplest whole number ratio of elements in a compound. Okay, and then what's this thing here? Oh, it is letting me draw now. But just not on that, I see. Okay, so yeah, this is down here. This is something called a general formula. So a general formula is the formula of a homologous series. The homologous series here is alkanes. Alkanes all share the same general formula, which is CnH2n plus 2. Like alkenes are CnH2n. So if all chemicals in a homologous series share the same general formula. Okay, next question is about isomers. Have a read, pause the video. State there are 2 isomers of C4H10. State what's meant by the term isomers. So this is just a bit of recall. So isomers, 2 marks. First mark, isomers have the same molecular formula, 1 mark. A different structural formula, 1 mark. Just remember this, or remember that. Comes up all the time. This isomers defined. You definitely need to have that in your brain really quickly, super easy. Okay, draw the displayed formula of each of the isomers of butane. Okay, let's take that over to my thing over here. Okay, so again, obviously pause the video. So butane formula, draw the displayed formula. So displayed formula is defined as showing every single bond. Okay, so the first one is literally, they've already pretty much given you it in the actual question. If we go up here, you see that? That's one of the isomers, that's butane. So you've got to draw that with displayed formula to show all those bonds. There's 3 bonds there, there's 4 bonds there, there's 3 bonds with hydrogen and 1 bond with carbon. This carbon is bonded to those 2 carbons on either side and the 2 hydrogens. So let's draw that. So we've got 4 carbons in a chain, and then we've got coming off them hydrogens. Students tend to sometimes leave out the hydrogens. Don't ever do that. You will definitely lose a mark. Even when you're practicing, students always tell me, oh yeah, in the real exam, I won't do it. But because you're so used to doing it, leaving them out in the real exam when you're stressed out, that's definitely when you will keep doing this. So just never do it. Never leave trailing bonds. Always draw the hydrogens if you're asked for displayed formula. Okay, and then an isomer. So an isomer has the same molecular formula, so the same number of carbons. So how could I arrange the carbons in a way that is a different structure but the same number? There's only one possibility. So if you don't quite understand isomers, this is actually a little bit tricky. So quite a few students might do something like this. They might put the C there, but that's actually the same molecule. It's just because carbons, the bonds can sort of bend a bit. So that wouldn't be a different isomer. That's wrong. Again, equally putting it down there, that's not an isomer, no. But it's here. The only possibility is here. Okay, and you actually are expected to name this. You're expected to know the name of simple isomers, basically unbranched isomers. This only has one part. This is called a chain isomer, where the chain length changes. And again, let's draw on all the hydrogens. We know how many hydrogens each carbon has because carbons must have 4 bonds. So look at all the bonds they already have and add more bonds and add more hydrogens. And then just do a little sense check, count them up, but they will add up to the 10. They will add up to 10. Okay, so there are 2 isomers. This one's called butane. This is called propane, it's called methyl propane. This is the methyl group, and this is propane. So this is methyl propane. I wonder if that's going to be a next question. No, it's not. Methane reacts with bromine to form bromomethane in one of our product. Pause the video. Okay, so now we're moving on to the reactions of alkanes and also possibly alkenes afterwards. So we're looking at methane reacting with bromine to form bromomethane in one other product. So this is just one, again, you need to know. You need to know that alkanes react with halogens under UV conditions, and the other product is always going to be one of the hydrogens being kicked off and getting with the other bromine. So it's going to be hydrogen. This is the formula, so we need to write HBr. We know it's HBr, not HBr2 or 2HBr, because bromine is in group 7, likes to form one bond. Hydrogen is in group 1, likes to form one bond, so it's just HBr. What is the name of this type of reaction? So you just need to know that when alkanes react in this mechanism, this is a substitution reaction, because the one of the hydrogens, let's maybe draw that. Here's the methane. Maybe let's draw it elsewhere. Can't draw there. Okay, here's the methane. Methane has, it's a rubbish methane, 4 hydrogens. And what's going to happen is the bromine molecule is going to come along, okay, and it's going to remove, so it's going to remove one of these hydrogens, and it's going to join on. So this bromine here is going to join on. This is going to go on there. Okay, and okay, where were we? So state the condition needed for this reaction to occur. Right, so we're talking about the substitution for this reaction occurring. I think I was drawing about it. I was drawing on a bond. So yeah, so we were showing how this reaction here, this bromine molecule Br2 reacts with the methane, okay, and then produces HBr in a substitution reaction. And then it says, state the conditions needed for this reaction to occur. That's just a bit of recall. You should know that alkanes reacting with halogens need UV light. So UV light. Oops. The UV light is there to break the bonds between the halogen to start the reaction off to form. We don't need that. Okay. When ethane burns in a plentiful supply of air, so do pause the video. Carbon dioxide and water are formed. Give a chemical formula for this reaction. Okay, so it's telling us everything. We just need to know, I guess we need to know what burns means. So when something says burns, it means we're reacting with oxygen. So I'm going to do this in the other, let's do it over here. Okay, so we got C2H6. Burns means adding to oxygen. So let's add an oxygen molecule there. And then we're producing, it tells us what we're producing, carbon dioxide, and it tells us we're producing water. So all we got to do is just basically write that out and then just balance the equation. So let's start off. When you're balancing equations, always leave the thing which is on its own. You see oxygen is not in a compound. Always balance that last. When you're doing combustion reactions, yeah, always leave the oxygen till last. So let's do carbon first, because why not? There's 2 carbons there. There's 1 carbon there, so let's put a 2 there. Carbon's balanced. Then we'll do hydrogen. There's 6 hydrogens there. There's 2 there, so let's put a 3 here. Now hydrogen's balanced. And now let's do the oxygen. Oxygen's a bit more tricky. So on the right-hand side, we've got 2 times 2, so 4 oxygens there. 3 times 1, so 3 oxygens there. So we've got a total of 7 oxygens. 7 oxygens. If you were doing this, sorry, I probably should have. The way we generally teach this is to write down all the elements on the side, count them all up. Yeah, but to be honest, you do need to get fast. This is quite a slow method, but it's a good method of doing it. Yes, you count all the elements up. You're like 2, you're like 1, and then you put the numbers in. But anyway, I'm not going to go through all that. Anyway, so we've got 7 oxygens on the right-hand side, and on this side we've got 2 oxygens. So what number can you multiply 2 to turn it into 7? So what do I have to times 2 by? If I times it by 3, that makes 6. That's not enough. Times it by 4, that's not enough. So I can times it by 3.5. 2 times 3.5 makes 7. 3.5, or you could write 3.5 would also be acceptable. That is totally fine to put fractions and decimals for this equation. Totally fine. However, if you don't like them, it is also totally acceptable to multiply everything in the equation by 2. If I times that by 2, then it becomes 7. So it will become 7, but I have to times everything by 2. So it will be 2, 7, 4, 6. So 2 of those, 7 of those, 4 of those, 6 of those, all both acceptable. Let's go back. When the air supply is limited, incomplete combustion occurs. Explain why a gas formed by incomplete combustion can cause a problem for humans. So the one they're trying to get at here, I mean, it's not actually that clear because there's a few ones which cause problems for humans. Maybe they'll accept multiple ones. We'll check the mark scheme later. But the one which is probably the most problematic for humans, because it kills us, is carbon monoxide. I'm assuming that's what they're getting at. So let's put our answer in here. So you have to just know that products of incomplete combustion are carbon monoxide, water, it's not harmful, and unburnt carbon particles are also a problem. Unburnt carbon particles, soot, and unburnt hydrocarbons are also a problem. But the one they're getting at here, I think, is carbon monoxide. It causes the biggest problem. It kills us. The unburnt carbon and hydrocarbons just give us like breathing difficulties, whereas carbon monoxide, CO, carbon monoxide, kills us. So carbon monoxide is a toxic gas produced in incomplete combustion. So I'm assuming you'll probably give us 1 mark for saying that. And then probably 1 mark for explaining why it's toxic. So why does it kill us? So it binds to hemoglobin in our red blood cells, preventing oxygen from being transported. I wonder if we go. We probably don't need to go that much detail. The fact that it's hemoglobin is not really relevant. You probably could just say red blood cells. Let's check the mark scheme and see what it says about that. Where were we? So first mark is, they want carbon monoxide. Interesting, they don't accept carbon soot, or even though they should. It's a bit unfair, but yeah, it's definitely the most dangerous one. And they're saying it limits the capacity of blood or hemoglobin to carry oxygen, or words to that effect. So what we said here is good. We're saying preventing oxygen from being transported. That's fine. Actually, if I had to rewrite that, I would say maybe not preventing or reducing the amount of oxygen transported, because it doesn't like prevent, but it reduces. But that would have got the mark. Okay. Let's move on. Question 4. Question 4 is about rates of reaction. Pause the video, have a look. A student investigates the effect of temperature. So we're looking at temperature. Let's highlight that. Temperature on the rate of reaction. So do try and just get into the habit of highlighting the key important stuff. 2 solutions. Reaction turns from colorless to blue. Give 2 variables that the students need to keep constant in this investigations. This is actually a practical style question, looking at the experiment of rates of reaction practical. Okay, so we are changing temperature, so that's our independent variable. We're measuring like time it takes. So time is our dependent variable, or rate of reaction. So we're measuring that. What do we need to keep consistent? So the student pours 25 of solution A into a conical flask. They've stated the volume, and they add B, and they measure the temperature. And they record the time taken for the mixture to turn blue. I don't know why I'm highlighting everything. Let's stop doing that. So one variable, very important variable that we must keep the same, is the concentration. So concentration, because let's think about the other things that affect rate of reactions. The other things that we're taught temperature, concentration. We are taught volume for gases, so pressure for gases, but there's no gases here. Surface area for solids, there's no surface area here, and catalysts. So concentration definitely must be kept constant. And basically there's temperature between 2 dimension occurs. repeating at different temperatures. So I guess probably keep the volumes the same. What else? Record the timetable emission term blue. Yeah, let's see what the mark scheme says. That might be just it. So, you get specific marks for saying concentration of A and concentration of B. But yeah, concentration and volume. Was I specific enough? I guess because they said A, I should have keep the volume of B. Yeah, maybe I wouldn't have got the marks. I didn't say volume of B. Allow amount of B solution. Amount is fine, actually. So I might have lost the mark there for not being specific. Really, really important to learn. You have to be very, very specific. Constant, not just concentration. Concentration of A and B must be kept constant. Okay. Let's move on to, oh yes, a very frustrating mark to lose if you lost it for not being there. Anyway, let's move on. So this is a graph question. It might be difficult for me to do on here, but let's try. So we've got some results here. Plot the results, just one mark. When you're plotting results, use a sharp pencil and do neat little crosses. Don't do dots, neat little crosses. Don't assume that you can rush through this. It's only one mark. I'll do it really quickly. The examiners will check precisely, and if it is not perfect, the mark scheme will say within one plus or minus one small square, you will lose a mark. It's such a silly mark to lose, but so easy to lose it. The points, so we can see these points here. We can see the line of best fit would run down here, down here, down here. So we can clearly see this is the anomalous result at 25. And it says give a reason for the anomalous result. Well, I guess they could have messed up by not starting the timer properly because it should be higher. So therefore, maybe they didn't start the timer properly, or measure the temperature. Maybe they didn't measure the temperature correctly. Maybe it's actually a higher temperature, because that would fit off if it was. That would fit if it was a higher temperature. Yeah, it would. So let's see the mark scheme. Yes, so high temperature higher than 25, or started the timer too late, took reading too early. Okay. Use your graph to determine the time taken for the mixture to turn blue at 55 Celsius. Okay, so we got to interpolate. So basically find 55. Okay, draw a line up to where your curve's going to be, and then it's probably going to be somewhere here. Interpolate it. I obviously haven't done this graph, so it's not correct, but you just draw it up to the line and draw it off. There will be some leeway here given. Let's see what they give. So do want you to make sure you're drawing the vertical line, so you do need to show it. Use your graph. You have to use your graph, so you can't just eyeball it. You do need to actually use it. And then the value, as long as it's sensible, you've used the ruler, you should get the mark for that. Oh no, the expected value should be between 150 and 117. Yeah, so somewhere around here. 115, 117, that's it. Okay, use the information from the table to calculate the mean rate of reaction at 20 Celsius. Give your answer in standard form. Okay, so use the information from the table to calculate the mean rate of reaction at 20 Celsius. And it tells us this equation here. It says mean rate equals 1 over time in seconds. So all we have to do is plug in our answer. So if you look at the table at 20 Celsius, it is 156 seconds. So it'll be 1 over 156. So 1 over 156. And then it wants it in standard form. Let's get our calculator out. Okay, so it comes out as 0. Am I writing in yellow? It's the awful color to write. 0. That's right over here. 0.0641 working to free SF. And we've got to turn that into standard form. Okay, so to turn it into standard form, we're seeing, so standard form is written between 1 to 9. So we're moving this basically here. And how many times have we moved the decimal point to get 6 there? So it's going to be 6.41. And you can see we've moved the decimal point 1, 2, 3. So that's going to be times 10 to the minus 3. It's always quite easy to turn a decimal into standard form because it's just basically count the number of zeros, and that's how many the 10 to the minus 3 is. So 6.41 times 10 to the 3. Okay, they're allowing it to 2SF as well, but yeah, probably 3SF would be more sensible here because. Okay, so explain how increasing the temperature affects the rate of reaction. So this is an answer you should get quite sort of familiar with. Very common question, always comes up. Explain how temperature affects the rate of reaction. So state the obvious first. So the obvious is that increasing temperature increases the rate of reaction. Increasing temperature increases the rate of the reaction because the particles have more kinetic energy. Okay, and then why is that important? Because we have more or higher chance of successful collisions. Terrible spelling. Yeah, so that's probably a great answer for GCSE. We could also add, this is a bit more advanced, that more particles have equal to or greater than the activation energy. I think that should be 3 marks already. Let's check the mark scheme. Okay, so where are we? So rate of reaction increases. Let's zoom in a bit. Rate of reaction increases, 1 mark. Kinetic energy of particle increases. You can just say particles move faster, but I think saying more energy is better. More successful collisions per second. Or did I say that? No. Okay, per second. I would have lost the mark there. You must say per second. That's what I always tell the students that, but I forgot that myself. You always must say per second. It's not just good enough to say more successful collisions. Allow more frequency collisions having high energy. So yeah, we've got a mark there anyway, but yeah. Yes. Okay, cool. Move on. Question 5. Question 5 is about organic molecules. We've got methanoic acid. Give the total number of atoms in 1 molecule of methanoic acid. So just count. Okay, it's quite easy. So 1, 2, 3, 4, 5. Okay, nice question. Determine the relative molecular mass of methanoic acid. Really nice question. Go to your periodic table. Okay, so you've got. Let's do this on my board over here. Okay, so going to the periodic table, we've got methanoic acid. Methanoic acid is CHOOH. So we've got 1 carbon. Carbon is 12 on the periodic table. 2 hydrogens. Hydrogens are 1, so 1 times 2. We're adding all of these up to get the MR. And then 2 oxygens. Oxygen 16, so 16 times 2. So what's that? 32, 34, 36, 46. Okay. That's right. 32, 44, 36, 46. Yeah. Okay. Explain why methanoic acid is not a hydrocarbon. Okay, so it's asking you basically to define what is a hydrocarbon and why does it not fit the definition. So what is a hydrocarbon? A hydrocarbon is defined as a molecule or compound, molecular compound, containing hydrogen and carbon only. So 2 marks. I think you need to define it. I think probably the mark will be, so what is a hydrocarbon? A hydrocarbon is a molecular compound. You can't just say molecule or compound containing only hydrogen and carbon. Carbon atoms. Okay, so the only part's really key. Okay, methanoic acid contains oxygen atoms. That's the one. Methanoic. Methanoic. Huh. Okay. And yeah, so I'm asking for that. Hydrocarbons contain only carbon, hydrogen. Methanoic acid contains oxygen. Yeah, we're good. The atoms in methanoic acid are held together by covalent bonds. State in terms of electroattractions what's meant by the term covalent bonds. Another definition you just need to know. This one comes up again a lot. I keep saying that, but GCSE repeats itself, and you need to learn the definitions. Just get a piece of paper, write them out, cover them up, and get them until you've got them perfect. So covalent bond, state in terms of electrostatic attraction what is meant by covalent bond. A covalent bond is the electrostatic attraction between. So all of their bonds are like this, start off with this sentence. What is an ionic bond? It's the electrostatic attraction between. What is a metallic bond? It's the electrostatic attraction between. A covalent bond is the electrostatic attraction between a shared pair of electrons and the nuclei of two adjacent atoms. So yeah, probably the mark will be for shared pair and nuclei. Let's check the mark scheme for that. So electrostatic attraction between nuclear and shared pair of electrons. Yeah, nuclei has to be plural because if you look at a covalent bond is between two atoms. So for example, let's look at a hydrogen bonded to hydrogen. Okay, here's one hydrogen atom. Let's draw the nucleus in red here. That's the nucleus. Okay, and then let's draw the electrons with a little green E. There's its outer electron. And then here's the other hydrogen. There's its nucleus. Here's its outer electron. Okay, and what happens in a covalent bond, the covalent bond is this shared pair of electrons. They're each sharing one. And there's an electrostatic attraction between the positive, this is positive, this nucleus, positive nucleus, and the shared pair of electrons of both nuclei. So this is positive here. So you've got this positive charge holding the negative charge in between, therefore holding the two atoms together. That is what a covalent bond is. Moving on. Draw a dot and cross diagram to show the bonding in a molecule of methanoic acid. 3 marks. Okay, cool. That's actually a bit naughty. I'm pretty sure they say in the spec that, yeah, they show dot and cross diagrams for the following molecules only. That's actually a bit unfair. But this definitely has come up before, actually, where they've asked you stuff outside of that. The spec, unfortunately, does lie to you occasionally. So, methanoic acid dot and cross diagram, not too hard. So you've got your carbon in the center. Let's just draw out the stick. It's a good idea to draw the stick diagram first. Okay, so the displayed formula first, I should say. And then we'll try and use that to work out its dot and cross. So we can see you've got these. I'm doing it completely wrong. Let's start that again. Oh my God. So methanoic acid, not methanol. Okay, here we go. So we've got the carbon here, we've got the oxygen here, we've got another oxygen down here, which is singly bonded, and a hydrogen over here, and we've got a hydrogen over here. Okay, let's draw some rings around them. Here's my carbon. And let's draw a little bit overlapping. Let's move that a bit closer. Do hydrogen in blue. Here's my hydrogen. Should be a bit closer, actually. There's different ways of doing dot and cross diagrams. I prefer this way because you can see which one is which atom. Let's do this oxygen here. Try to keep them same consistent size. Failing a bit on that, but oh well. Let's move this. That's fine. Okay, so we've got all these overlapping circles showing the outer shells. Now let's put the electrons on. Let's start with this hydrogen. Hydrogen only has one electron. Let's draw it there, cross. Now, as this is cross, the next atom it's bonded to must be represented by dots. It's a dot and cross diagram. It's never going to be a cross and cross diagram. So this is a cross, this has to be a dot. So carbon has 4 electrons in its outer shell. I know this because it's in group 4. I know hydrogen has 1 electron in its outer shell because it's technically in group 1. Oxygen has 6 electrons in its outer shell because it's in group 6. Anyway, let's do so. Carbon's got 4 electrons. It's got 1 here. So we've got 2 left. But can you see there's a double bond? There's a double bond between the oxygen above. So we need to have 2 electrons. Each atom is sharing 2. So there's my dots. Now, because this carbon is dots, this oxygen has to be crosses. Now, oxygen has 6 electrons. So let's draw the double bond first. So there's 2 pairs for the double bond. And then it's going to have 4 extra electrons, which live in pairs. Let's put them as far away as possible from each other because they're all electrons, they're all negative, they all repel each other. Let's move on to this oxygen down here. Let's put the electron for the covalent bond, the shared pair of electrons. It has got 6 electrons. Let's put its electron here with its covalent bond. And again, it's got 2 left over, which live in pairs, trying to get as far away from everything else as possible. And then finally, we've got to do this hydrogen. Now, this hydrogen has to be represented by a dot. Just because this one was a cross is meaningless. This is crosses, so this one has to be a dot. Let's draw it there. And there we go. That's our dot and cross diagram for methanoic acid. Calculate the empirical formula of the organic compound with composition by mass. This one. Okay, cool. So we've got an empirical formula question now. Let's do this one. So this one is like so. So we want to calculate the empirical formula. Empirical formula, what you do is you calculate the moles. So to calculate the moles of each of the chemicals, you are going to go, so moles equals mass over MR. But we haven't got the masses. Well, pretend we do. If they ever get given percentages in an empirical formula question, just pretend that these are grams. Or you could imagine what happens if we had 100 grams. If I had 100 grams and 52.2% is carbon, how many grams do I have? Oh, obviously 52.2 grams. So just pretend these are all grams. So we know the masses of each of them. We can use the periodic table to work out the MR. So the MR of this one is 12. MR of this one is 1. MR of this one is 16. Okay, so let's put that in and work out our our moles. So 52 divided by, let's do it here, 52.2 divided by 12, 4.35. Don't round. That's divided by 1, so just 13. Okay, this is going to come up to 1.9 something, is it? 34.8 divided by 16. Wait, now my math sucks. Of course, 2175. 2.175. Okay, we've got the moles. Moles are the ratio. This is telling us the ratio between these chemicals. It's telling us that for every 4.35 carbons, I have 13 hydrogens and I have 2.175 oxygens. But it's giving me a ratio with decimals. I don't want a ratio with decimals. I want a whole number, whole numbers. Okay, so how do I turn these into whole numbers? Simply divide all of them by the lowest one. Which one's the lowest one? This is the lowest one, 2.175. So divide all of them by 2.175. So what is 2.175 divided by 2.175? 1. 4.35 divided by 2.175? 2. 13 divided by 2.175, I want to say 6. Let's put that on the calculator. Does it come out exactly? 13 divided by 2.175. Doesn't come out exactly. It comes out as 5.977. But at this point, because we're calculating empirical formula is whole numbers, we round that to 6. So 5.977 rounded to 6. Okay, so there's our ratio, 2 to 6 to 1. So what's the empirical formula? Well, the empirical formula is C2H6O1. We don't need to write the 1. Just write, oops. C2H6O. So we can see this is the empirical formula of ethanol or butanol or hexanol. Okay, wicked. Where are we at? Question 6. Which element is a liquid at room temperature? Memory, just memory. Just need to know. Bromine. There's not many liquids. There's not many liquids at room temperature. Bromine, mercury, technically francium. The rest, these two are gases. There's not many gases. The gases you need to remember, the way I always teach my class, for the gases, for the elements, it is hydrogen, nitrogen, oxygen, fluorine, chlorine, and group 0. Hydrogen, nitrogen, oxygen, fluorine, chlorine, and group 0. All the group 0s, noble gases. That's the only gases. So therefore astatine, everything else is a solid, so astatine must be a solid. What color is solid? Iodine, memory. Okay, so iodine is dark gray. It's actually not dark gray. It's quite metallic-y, but that's the most closest to it. I would say it's more light gray, but it's sort of dark silvery gray. Anyway, it's definitely not black. It's definitely not dark brown. Definitely not purple. Confusingly though, however, as a gas, it is purple. It is purple as a gas. In solution, when it's dissolved in solution, it does look dark brown or even black. So actually I can see why you get these ones confused. Yeah, but as a solid, I would say a gray, a silvery gray, dark solid. Anyway, dark gray is the best one now. Describe a test for chlorine gas. Again, just memory. Okay, so what's the test for chlorine gas? So for chlorine gas, you hover some damp blue, red, it's acidic, so red. So damp blue litmus paper. So hover damp blue litmus paper over the gas. The blue litmus paper turns red and then gets bleached white. I wonder if you need to all that, but definitely it might be okay for just, it may be okay just saying, why can't I move this here? Let's see if you actually need to say how they're bleached as well. I feel like you do. Where are we at? Yes, you do. So you need to say, test with damp blue litmus paper, although that is in brackets. If it's in brackets, you don't need it. So actually just test with litmus paper is allowed. Or universal indicator paper will work. And they're accepting red turns bleaches turns white. That's interesting. They're not accepting they're not accepting it goes blue first. That's been in previous mark schemes. But anyway, yeah, it goes blue and then it bleaches white. But actually, to get the mark, you need to say bleaches white. Interesting. I need to make sure we highlight that more on our slides. But that's the most important part now. This is obviously being a recent paper, mark schemes do change, so we need to make sure we're learning what's in the examiner's head, where their thinking is, what they want to give us marks for, not necessarily what they previously gave us marks for. Okay, sample of chlorine containing 2 isotopes has percentage composition. So this is a relative atomic mass question. Let's go and do this. Okay, so here we go. So to do this, the equation you need is relative atomic mass. Oh, and whenever you're doing maths questions, always just check, have they talked to you about decimal places, and underline it if they have. Must. Maybe even put where your answer is going to be. So my answer is going to be down here. I'm going to write down 1 dp just to remind me, because it's such a stupid, annoying mark. Like you always kick yourself. Like I do it all the time when I've done a question and I lose a mark for decimal points and sig figs, when it's so obviously tells you in the question. But when you're stressed in an exam, it's so easy to do. You don't want to lose that mark. That mark could be the difference between the grade. Okay, so what's the equation? Relative atomic mass, or given the symbol AR, equals mass isotope 1 times percentage abundance plus mass isotope 2 times percentage abundance plus mass isotope 3 times percentage abundance plus, if there's 4, they probably won't give you that like 4, but you could just keep going on. You keep adding them. This time we've only got 2 isotopes. Let's call this one 1. Let's call this one 2. Okay, so let's put the numbers in. What's the mass of isotope 1? Well, it's a number. It's chlorine 35. 35 is its relative. If it is its not relative, it's atomic isotopic mass. So its isotopic mass, its isotope mass is 35. Its abundance is 71.2 plus next one 37 mass times abundance 28.8. Okay, calculator. Obviously, you need to show you're working here. You can't go to the periodic table and just assume that it's going to come out to what the periodic table says. Okay, so 35 times 71.2 plus 37 times 28.8. Oh crap, I forgot to, I have to divide the whole thing by 100. So this whole thing, because it's percentages, adds up, so you have to divide the whole thing by 100. And that's always going to be the case in GCSE. It's always going to be percentages, so you always divide it by 100. Okay, so what did I get? Divide by 100. And that's come out as a weird answer. Let's check that's right. 35. Those numbers are a bit weird actually, because chlorine is really 75%, not 71. Anyway, let's just do that again. Yeah, I think this is just meant to come out as a weird answer. Let's just check though. 37 times 28. So this is what I do. If I was in a real exam, I would double. If I came out a weird answer, I know. Oh no, I think I must have done a calculator error then. Yes, come out to a more sensible answer. So I just must have made a mistake in the calculator. 35 point. It's coming out as 35.576, but it wants it to 1 decimal place. So obviously that 7 closes that 5 to turn into a 6. So there's my final answer, 35.6. Let's check that's the correct answer, and I haven't made any more calculator errors. Yeah, we're good. Okay, where are we at? C. A student is given an aqueous solution of chlorine, an aqueous solution of sodium iodide. Explain how the student can use these solutions to compare the reactivity of chlorine with the reactivity of iodine. Okay, 4 marks. Okay. So we're given an aqueous solution of chlorine and an aqueous solution of sodium iodide. Explain how the student can use these solutions to compare the reactivity of chlorine with the reactivity of iodine. 4 marks. It seems like a lot of marks for not much to say. Let's start writing and figure out where the marks are. Right, so we've got to explain how we can compare the reactivity of chlorine with the reactivity of iodine. We know that chlorine as a molecule is more reactive than iodine. So therefore, the chlorine molecule, the atoms in the chlorine molecule, will displace the ions, the iodide ion. So explain how the student can use these solutions. I guess we'll explain. The student, so we're not explaining, we're explaining how the student should take a test tube of sodium iodide and add some chlorine, and observe the color. Observe the color, which should be colorless. So all of these salts in solution, if you can't remember, they're generally colorless. In fact, the only one that you guys really need to remember is not colorless in solution copper. Generally, a lot of the transition metal salts are coloured, but any of the non-transition metals, sodium, group 1, group 2, are colourless. Anyway, so we've got a colourless solution of sodium iodide, and add chlorine solution, which is also colourless. Or if it was very concentrated, might have a faint greeny yellow tinge to it, but that's probably too dangerous to use. Okay, the chlorine will displace the iodide in the sodium iodide because chlorine is more reactive, and we will see iodine appearing in the solution, which we talked about iodine earlier, iodine in solution, which looks dark brown. Explain how the student can use these solutions. I don't know what else I would write. Let's think of where we put the marks. So let's just go to the mark scheme and see what they say. So what we got? Add chlorine solution to sodium iodide. Yes, we said that. Solution turns brown. I said dark brown, but fine. Iodine is displaced. Did I get the word displaced? The chlorine, I did. Chlorine will displace the iodide because chlorine is more reactive. Okay, yeah, so we have got it all there. That we added maybe. It's fine. Just have a look and see on the disallows. Reject incorrect use of iodide or chloride once only. Yeah, you've got to be really careful with the words. So let me draw it over here. So iodine is I2. That's iodine. Iodine. Chlorine, Cl2. That's chlorine. When they form in an ionic salt like sodium iodide, it's now in its ion form. This is technically, and it's a negative ion, so we call it iodide. Iodide. And again, when chlorine displaces it, it's going to go into its negative form. It's going to form sodium chloride, not sodium chlorine. So you've got to be really careful with your spelling, your use of iodide, iodine, because you lose marks. What else? Yeah, just state the obvious, mix them together. Some people might miss that out because it's so obvious, but you need to state the obvious in an exam. Let's move on. Okay, a teacher ignites a piece of magnesium ribbon, places it in a gas jar of oxygen. This is the equation for the reaction. Give 2 observations that we made during this reaction. Okay, so this is topic, looking at topic we teach this. Group, when did we teach this? Just combustion, I guess. Metals, group, we talk about group 1 things reacting with oxygen there. Yeah. Anywho, so 2 observations. Well, we're going to form magnesium oxide. So what does that look like? Well, magnesium is a silvery metal thing. Oxygen is a colorless gas. And magnesium oxide is, I want to say, of course, this is one of the practicals that you're actually meant to do in amount of substance. That's when we do it. So magnesium oxide is a black solid, I think. So we'd see appearing. We'd also see a bright, before that appeared. Is magnesium oxide black? It's not. It's white. White. A white solid. Generally, again, most non-transition metal salts, oxides, are often just white, like they're colorless in solution and white. And we'd see a bright, really bright, so bright, in fact, I had my eyes the other day looking at it when I was burning it, bright flame, bright white flame, bright white flame, when we're burning it, and then we see a white solid. I hope I have got the right color there, pretty sure I do now. Yeah, white powder, white flame. Allow grey, white smoke, ash. Okay, cool. Okay, teacher demonstrates the reaction between aluminium and iron oxide. Oh, it's one of my favorite experiments. This is thermite. So state what is meant by the term exothermic. Okay, so what's exothermic? Again, just memory. GCSE is so much. It's just memorizing a bunch of stuff. It's not much. Like in A level, you have to like understand stuff and work stuff out. This is just, do you know what the word exothermic means? Do you know what this word means? So exothermic is when more heat is released than is taken in. Although, to be honest, you could probably just say exothermic is when heat is released is fine. I think you wouldn't only say then taken in. Let's see what it says in the mark scheme. Yeah, just gives out heat. Give a chemical equation for the reaction between aluminium and iron oxide. Okay, so I'll do this in the other thing. What does it tell us? It tells us we've got aluminium oxide. Does it tell us the products? The products are iron. So it tells us, if you've ever asked to give a chemical equation, often, pretty much always in GCSE, they always tell you what is being produced. Just have a look in the question previously to see, have I been told what's being produced? I mean, it's quite obvious what's going to be produced, but if your chemistry is good, but if it's not, just have a look, and even if it is, just check. Okay, so chemical equation, aluminium plus iron-free oxide. So the 3 tells us that iron is in its 3+ state. Okay, oxygen is always in its 2- state. Therefore, we can see the common multiple between those is 6. So therefore, we need 2 ions to turn that into 6, and we need 3 oxygens to turn that into 6. So it's Fe2O3. Iron-free oxide is Fe2O3. Okay, it's going to make aluminium. No, it's not. It's going to make iron. And it's going to make aluminium oxide. Aluminium oxide will have the same formula because aluminium is also 3+. And then we just balance it with a 2 there, 2 there, and it's balanced. Sorted. Explain why this is a redox reaction. So redox is when oxidation and reduction occur. Okay, so you can see in this example here, the aluminium is gaining oxygen, so it's getting oxidized, and the iron is losing oxygen, so it's getting reduced. So I would say here, I'll just say what I just said there basically. I would say, oops, square box. Aluminium gains oxygen, so it is oxidized. And iron loses oxygen, so it is reduced. You could also talk about electrons here, but it's not no need. Maybe just add a redox reaction. Yeah, I think I would add this definitely. A redox reaction is one in which both oxidization and reduction occur. Let's check the mark scheme. Yeah, aluminium oxygen gains oxygen, so it's oxidized. Iron loses oxygen. Iron oxide loses oxygen, except iron. Or aluminium is oxidized and iron oxide is reduced. Interesting how it's not clear whether they would accept, because I've said iron loses oxygen, which is technically true. I think you would get the mark for that, but now, because when talking about electrons, it's iron which is going to be gaining electrons, not the iron oxide, but they said iron oxide. Iron oxide, would I tell you to use that? I guess you've got to try and, as I said, get into the examiner's head. I'm not sure I like this, but you would still get the mark for this. Almost certainly you would, because it's correct, but iron oxide loses oxygen, so it's reduced. Okay. Okay, so the mass of magnesium oxide is less than expected. Okay, it's less than expected. Describe what the students should do to obtain a more accurate mass. Let's go back to their experiment. So they're heating this up and they're trying to find the mass of magnesium oxide. And what they haven't done in the description is they've heated it for 5 minutes and then find the mass of the magnesium. But they haven't ensured, how do we know all the magnesium's actually reacted? So how do we know it's actually reacted? So what they should have done is then heated it, so weighed it, heated it again for like 5 minutes, weighed it again. And if the mass is now the same as before, we know that all the magnesium has reacted. But if the mass starts to increase more, we know that the reaction hasn't finished. So basically, you keep heating until you get two masses which are the same. It's called heating until a constant mass. So to get 2 marks, I would probably just say heat again for 5 minutes and reweigh, repeat until constant mass achieved. Okay. Okay, question 8. This question is about group 4, oxides, lead carbonate heated, lead oxide formed. Give the name for this type of reaction. Okay, so you can quite easily tell what type of reaction is by looking at how many products, how many reactants there are. So there's 1 reactant and 2 products. So we must be breaking something up. This must be getting broken up. So the word for that is decomposition. So this is and the solids don't just break up on their own. So I think I think decomposition would get the mark, but it's technically thermal decomposition. So it's going to break up due to heat. Let's see the mark scheme, what the mark scheme says. Actually, I assume it's just decomposition. Yeah, just decomposition, thermal in brackets. Okay, cool. Okay, cool. A bit of maths. Okay, calculate the maximum mass. Okay, so let's do that. Okay, calculate the maximum mass. How many marks was this? This is worth 2 marks. Oops. Maximum mass of lead oxide. We've already got the equation. Let's just grab the equation here. So that's all we need to do. Here. So I always teach my students when they're doing questions like this, start off by doing a tick and a cross. So tick and a cross. What are they asking us about? They're asking us about calculate the maximum mass of lead oxides. That's that one there. So put a question mark out in front of that. That's the one we want to calculate. And they've given us information. They've given us the mass of lead carbonate. To put a tick next to that. Then always, when you're doing these type of questions, this is a reacting masses type of question. Basically, you're expected to work out moles, use moles to work out moles of something else, and then you work out mass. So always work out the moles of the tick. So we're going to show good working out moles of lead carbonate, I'll put 3 in a second, equals mass over mR. Let's draw that in. So put 3 there. Okay, so the mass 5.34 over mR. They luckily give it to us, so just 2, 6, 7. Although it's sometimes nice when they don't, because then they give us a mark for it. But well. Okay, so let's grab a calculator. Okay, so 5.34 divided by 267, 0.02 moles. Okay, once you've worked out the moles of the tick, this is the tick, right? Use the moles of the tick, use the molar ratios to work out the moles of the question mark. So can you see how the ratio between this and this is a 1-to-1? Therefore, and do write this down, don't just move on to the next step. Secure the mark, be like moles, mole, lead oxide equals 0.02. This is a 1-to-1 ratio. If it wasn't a 1-to-1 ratio, say it was 3-to-2, say this was 3 and this was 2, I would go 0.02 divided by 3, divide by the one you're at, times by the one you're going to. So divide by 3 times by 2. But it's not, it's a 1-to-1 ratio. I mean, I still do that. It's just, I go 0.02 divided by 1 times by 1. Obviously, it equals the same thing. Okay, and now I haven't been asked for the moles, I've been asked for the mass. So what does mass equal? Well, mass of this lead oxide. Always say what you're talking about. Always be clear. Mass equals Mr. Moles, MR times moles, moles is N, equal sign underneath, MR of lead oxide 223 given in question, times the moles 0.02. So that's going to equal, I divided rather than times 0.02, 4.46 grams. Okay. Check how many calculators. Yeah, that's good. Okay, diagram below shows lead carbonate. Complete the diagram to show what needs to be added to the apparatus to test that the gas released is carbon dioxide. 2 marks. Okay. So we got to, let's move my face out of the way. Let's grab this. Okay, so, well, we need to test a gas. What do we use to test for carbon dioxide? So the test for carbon dioxide, again, a bit of memory, is lime water. So we need to bubble the gas through some lime water. So there's a couple of ways you could do this, but I'm going to draw it like this. I'm going to do a beaker here, and in here, I'm going to put my lime water. Lime water. Lime water is calcium oxide. Okay, and then I'm going to attach a pipe like so. I'm going to have one which sticks up like that. I'm going to make sure that I don't get too artistic with it. I'm not going to put shading on it. This is meant to be like an engineering diagram. It's quite hard for me to draw because I'm doing it with a mouse, but this is what you don't. If you start putting shading stuff, you will lose marks because this is meant to be a schematic showing that there is. It's meant to show that the gas can get through here, through here, through here, through here, and in here. If there's any lines blocking it, then it's going to explode. Okay, and you will lose a mark. Okay, and then over here. Actually, I don't know. That's all I need to do, actually. I just need to bubble it through the lime water. I don't need to do anything else. I was thinking about putting a test tube there, but it's not what the question's asking. Yeah, so this will work. Bubble it through lime water, and the lime water should turn cloudy or white precipitate should form. So I think that will be enough for the marks. Let's check the mark scheme. So diagram showing a delivery tube. So that's a delivery tube. Did it ask us to label it? Actually, I didn't check. Some do always check because often they say label it. They haven't, so we're good. But yeah, you'll lose a mark if you don't label it. So you reject if sealed with, but you could lose a mark if it's sealed with anything. And lime water labeled. Did we do that? I think we did. Yes, lime water. Complete the diagram to show what needs to be added. Yeah, I guess because you need to show what, you obviously show that it's lime water. If you just did the diagram without saying lime water, you wouldn't get the mark. Lime water labeled. I did say that, but I didn't write that. I should have written the lime water. Complete the diagram to show what needs to be added to the apparatus to test the gas. It's a bit unfair, that, actually, because it's saying complete the diagram, but then it's saying you actually have to say, it's not really, but again, we're trying to learn what's in the examiner's heads. If the examiners ask a question like this, it's always better to put more information. So turns white precipitate. So, sorry, I should say forms a white precipitate. Don't ever write, I was just about to do it then, I sometimes write PPT is for precipitate. They don't like that, the exam boards. You need to write the full word, but I'm actually running out of space here, so that's going to say precipitate. So forms a white precipitate, or you can say turns cloudy, milky. Okay. Oh, the result of the test. Yeah, I was thinking that was so weird, them asking for that in that mark. The result of the test is a separate mark. Let's go back to the mark scheme. So you get 1 mark, the diagram showing, where's the second mark? This is confusing me. There's 2 marks there, but the mark scheme is saying 1 mark. Oh, I see. Oh, wait, that's mark. So lime water later for mark 2, and then turns or white precipitate forms for the second question. Got you. Okay, moving on. Silicon dioxide and carbon dioxide both contain covalent bonds. Silicon dioxide is a solid with a high melting point. Carbon dioxide is a gas at room temperature. Okay, explain why silicon dioxide has a much higher melting point than carbon dioxide. So when you're looking at non-metals, we know that non-metals have covalent bonding and can either be simple molecular or macromolecular. Most of them are simple molecular. The only ones you need to remember that are macromolecular are diamond, graphite, and you don't need to memorize this one because in the spec it doesn't mention it, but I always tell my students, always also remember that silicon dioxide is also macromolecular. Now, you're not actually meant to know that, but it's just really good to remember. But the reason this question sort of allows you to work it out, but it's a bit unfair if you've never heard it before, is the fact it's telling you it has a very high melting point. Now, that's a bit unfair. If your teacher had never mentioned silicon dioxide being a macromolecule, I'm not necessarily certain you would get that from that. I don't think it's fair. I think it should mention it in the spec that we just teach it that silicon dioxide is a macromolecule. Other ones they occasionally use are silicon on its own. So silicon, the metal, not the metal, sorry, silicon, the non-metal metalloid, is also a macromolecule, and also germanium. Those are the only three which are not mentioned in the spec, which they love talking about. Silicon dioxide, most common, silicon, germanium. Of course, there are other ones, but they don't really mention them often. Okay, explain why silicon dioxide has a much higher melting point than carbon dioxide. So 6 marks. Right, so 6 points. Refer to structure. Let's highlight that. Refer to structure and bonding. So let's start off by listing the structure and bonding for both of them. Let's go. Here we go. So silicon dioxide has a macromolecular structure. Don't say is a macro. You could say is a macromolecule. That's okay, actually. But it has a macromolecular structure. Why did I spell that wrong? That's right, I think. Macromolecular, yeah. Okay, whatever. So that's 1 mark. That's the structure. And has covalent bonding, although it does tell you that already, so it's not a mark for that. Okay. I mean, it does say refer to structure and bonding, so let's just leave that in there, but I don't think that would be worth a mark. Okay, we're going to come back to this sentence, but I'm just going to start off the other one and get the structure without the other one. So carbon dioxide. Carbon dioxide is also a non-metal, and a non-metal, so it's not a macromolecule, so it must be a simple molecule. So carbon dioxide has simple molecular structure, or you could say is a simple molecule. That'd be worth 1 mark. And also has covalent bonding. They've said to mention bonding. It's not a mark for it though. I'm just going to say it. Okay. All right, let's go back to this one. Why does it have a high melting point? Well, macromolecules, when you break a macromolecule, you're breaking the many strong covalent bonds. There's millions of them. The silicon dioxide has millions and millions of many strong covalent bonds. All of them we have, well, most of them we have to break, a lot of them we have to break to melt it. So to melt, we must break the many strong, these are keywords, covalent bonds. And then between, always say between, what are we talking about? We're talking about strong covalent bonds between atoms. So many strong covalent bonds. This is definitely worth a mark, possibly probably two actually. Many strong, I reckon there's probably one there, and maybe one between atoms. Therefore, requires a larger, let's be comparative, because we're asked to explain, higher, larger, therefore requires larger amount of energy to break. Yeah, there will definitely be a mark for energy. Carbon dioxide has a simple molecular structure. It also has covalent bonds. They've asked us to mention that, but they're not relevant when we're talking about melting point. When you melt a simple molecule, you do not break covalent bonds. I'll say that again because everyone gets it wrong. When you melt or boil a simple molecule, anything with simple molecular structure, you do not break covalent bonds. When you melt a macromolecular structure, you do break covalent bonds. You cannot get these things confused. You will lose a lot of marks if you get these things confused. If there's one thing you must remember, it's that. So carbon monoxide, you're not breaking covalent bonds. To melt, we must break the weak intermolecular forces between the molecules. We must break the weak intermolecular forces between the molecules. Therefore, this requires less energy to break. And we've already said energy comparative up there, so you only get 1 mark, I'm assuming. So how many marks do I think I've probably got? It looks like a 7. Sometimes mark schemes do have that. Let's check the mark schemes here if we missed anything. So silicon dioxide has a giant covalent structure. I say macromolecular. Generally, the mark schemes were using macromolecular before. They mean exactly the same thing. You will get exactly the same mark for macromolecular. But it's just interesting that they've changed their language. Giant covalent, fair enough. We can start using that. Covalent bonds are very strong. So you see we said that. So macromolecular structure for Mark 1, strong bonds for Mark 2. Silicon dioxide, many bonds need to be broken. So you see many strong bonds need to break. A large amount of energy, more energy. That's the sentence down here, more energy. And then moving on to carbon dioxide has simple molecular structure. So simple molecular structure. It has weak intermolecular forces between the molecules. The forces between the molecules are weak intermolecular forces. And they are, it's for some reason, there is a 7th mark, even though it's literally the same as, or the opposite of that one, less energy. But anyway, only need 6 marks, so brilliant. And hopefully that's it. Oh no, got question 9. Okay, cool. A student uses the reaction between zinc powder and dilute nitric acid to prepare zinc nitrate crystals. Right, so we're trying to make zinc nitrate crystals. That's that. Complete the equations. Just state symbols. So what's zinc? Zinc is a metal, so solid. S. Nitric acid. GCSE. Whenever we talk about acids, we mean solutions. It's not actually always true in reality in chemistry, but for GCSE, if you think acid, we think a solution, so AQ. It tells us that we're making crystals. Crystals are solid. Crystal means solid, so therefore this must be solid. And we should know that hydrogen, we talked about that earlier, that hydrogen is a gas. State what the student would observe during this reaction. Well, what happens when you see a gas being produced? You see bubbles, and what color is it? Precipitate. You see a solid precipitate forming. I imagine you probably get 1 mark for either one of those. Look. Bubbles. Ignore crystals form. Why are they not giving the mark for that? A student uses the reaction between zinc powder and dilute nitric acid to preserve zinc nitrate crystals. Oh, I have messed up. They are not. The fact that it says zinc nitrate crystals doesn't mean necessarily that they're forming in one step. So actually, in reality, I'm being very stupid here. Any nitrate that it is not a solid. So nitrates are all soluble. I remind you of the solubility rules. So anything with a nitrate in it is soluble. Anything, so most halides are soluble. Chloride, bromide, all these iodide, these are all soluble, except for silver. One's silver of lead. Anything with silver and lead, that'd be insoluble. Anything with sodium, that's meant to be Na. Plus potassium, ammonium, any ionic compound with these things is soluble. And then things which are insoluble are things like your carbonates, obviously not if it's sodium carbonate, potassium carbonate, ammonium carbonate. Your hydroxides are generally insoluble. Again, not sodium, not potassium, not ammonium. So you just need to remember your solubility rules. Let's go back to the question, which I forgot. Well, I got tricked. Okay. Anyway, yes, we're not going to form a precipitate because it's going to be in solution, so it'll be a colorless solution. So bubbles and colorless solution, or fancy word for saying bubbles, is effervescence. In preparation, the student adds excess zinc powder to dilute nitric acid and explain why the zinc is in excess. So we use excess zinc to ensure that all of the acid reacts, to ensure that all the limiting factor, acid, reacts. Why do we want all the acid to react? Why don't we just add excess acid so all the zinc reacts? Well, it's very easy to remove an excess solid. It is very difficult to remove an excess solution. So we ensure that the zinc is in excess because it's easy to remove. That would be the next step. And the answer is just to ensure that all reacts. To ensure that, I should say, so ensure that all, yeah, I said acid reacts. Describe what the student should do next to obtain pure dry crystals. Okay, cool. So this is making, oops, we're trying to make a soluble salt. So we've added our excess. Okay, so right now we've got a situation that looks like this. Let's draw it out. We've got a beaker. In the beaker, we've got, what the hell are the chemicals? Zinc. We've got zinc powder. There's excess. You're going to see bits of zinc floating around. Lots of it's hopefully already reacted with the nitric acid. Okay, so there should be 0 nitric acid left over in here because it's all reacted. So there should be zinc solid. There should be some of the product, zinc nitrate. Hopefully lots of it. There'll be no hydrogen gas because the hydrogen gas is all like coming off. So all the nitric acid's gone. That's all gone. And we've got bits of zinc solid. So, and we also got water. We've got water. So we need to remove, we want this. We want it to turn into a solid. Right now it's aqueous. So we need to remove the excess zinc and then remove the water. So let's remove the excess zinc first. How do you remove a solid from a liquid? So to remove the excess zinc, we should filter the mixture. Do anything before that. Let's heat it. Let's see how many marks we get. I might put, always, why not? It's always good to add more extra X. I don't think there's been a mark for this, but why not? Let's put it down. It's not wrong. Heat the mixture and stir, just to really ensure that zinc reacts. Okay, then to remove the excess zinc, we should filter the mixture. And then what do we want? We want pure dry crystals of zinc nitrate. Pure, it hasn't said, oh, it does say pure. So the fact that it's pure means we have to do something. Okay, so what we're going to do is we're going to heat the remaining mixture. So at this point here, we filtered it, so we've actually removed all the zinc. So all that's left now is water and our product, zinc nitrate. So we're going to heat it to remove some of the water. Heat the remaining mixture to remove some water until you see crystals. Right? Start to form. Okay. Then we are going to cool the mixture down to allow more crystals to form. Then we're going to filter the solution and collect the crystals. And then we're going to dry, we're going to wash it. Let's just add that as well. We're going to wash, why not? I don't think it's a mark, but wash the crystals in the filtering process. So what I want you to, if you've got your filter like this, you've got your crystals on top, just wash it with a bit of distilled water, distilled water, and then we're going to dry the crystals in a chemical oven or somewhere warm. Okay. 5 marks. Let's see how many we got. So filter off the excess zinc. That's that one there. Mark 1. Heat the solution until crystals appear. That's there. Leave the solutions to cool to crystallize. Filter off the excess clean crystals, allow it to dry. Brilliant. So we added a bit more detail, but more detail is fine. Okay, cool. Let's just check. Yeah, that's cool. Okay, formula for the zinc crystals is so it's a hydrated crystal. You can see there's 6 water molecules for each zinc nitrate. Complete the equation. Let's do that over here. Okay, cool. So it's telling us what's formed when zinc nitrate crystals are heated. The products are zinc oxide. Zinc oxide. It's weird they don't tell us the Roman numeral. They should. I mean, it only forms a 2+ ion, but it's a bit mean that they haven't. They should write zinc 2 oxide, really. I guess, is that in the spec that zinc is 2+ for you guys? Check. Anyway, it tells us what's formed. We just have to balance it. Students always get really confused by these equations. Like, oh, what does it form? It's like, look at the question. It literally tells you everything that forms. Zinc oxide, the only thing was maybe problematic finding out the formula for that. Zinc is 2+, oxygen's 2-, so it's just zinc oxide 1-1. Okay, it tells you. Now you've got to balance it. Okay, so 2 there. They've put a 2 there, so that has the. We can't change that. We can't change that number. That's a 2, so we'll put a 2 here. Okay, so zinc is now balanced. Let's balance water. There's 6 there. So we know that, 6 times 2, sorry. So that's going to be 12. This 2 here will multiply everything to the right by 2, so it's going to be 12. So we need 12 waters. That's a 12. Doesn't look like it. Okay, what's left over? Nitrate. You see there's 2 nitrates, but there's 2 lots, so there's 4 nitrates. So I'm going to need 4. You see there's 4 nitrates there. And then how many oxygens? How many oxygens? Okay, this is a little bit tricky. Let's count them up. So oxygens. We have got 2 times 3 is, we ignore the waters because the waters have all gone over there. So 2 times 3, that's 6, but times 2, so 12 oxygens. However, 2 are here, and 4 times 2, 8 are here. So there's 8 oxygens in there. There's 2 oxygens here. So how many left over? Well, 2 are left over. 2 oxygen more atoms. So therefore we need a 1 there. Or you don't need to put a 1 there. That's actually relatively difficult, actually. I think a lot of students would have struggled with that, working out the oxygen number. Yeah. Anyway, that's tough. It's hard to say how to improve on that other than just keep practicing writing equations. It's not a skill where there's a simple fix like, oh yeah, just do that. It's just question 10. Question 10 is about calorimetry. We're dissolving something, ammonium nitrate, in water. Give 2 reasons why they stir the solution. So we stir the solution when we're dissolving something in calorimetry. We want the reaction to happen as quick as possible. Because the slower it happens, the more error we get. So we want to stir to ensure that the ammonium nitrate dissolves quickly. And also to keep the temperature of the reaction even. What's the word? Even. Just equal. Keep the temperature of the reaction equally dispersed. What did they say? Let's look at the mark scheme. So the temperature is even throughout the solution. Allow heat transfers evenly. Equal, even. Okay. The diagram shows the minimum temperature of the solution. So this is obviously complete the table, giving the missing values, give your answer. Just really be careful when they say to the nearest 0.1, make sure you actually do it. Okay, so complete the table. This is the minimum temperature. That was the initial temperature. So read the thing. You see, that's 15, that's 20, it's going down. So that must be 16, 17, 18, 19. So there's 19 there, there's 20 there. Okay, so there's 4 graduations in between. So it must be 19.2, 19.4, 19.6, 19.8. So let's do it. So it must be 19.4. I'm surprised at how many students mess these up, these questions. Like, I think anyone can do it. Just when you're stressed and you're trying to do it fast, just take your time. It's 2 marks here, isn't it? So no rush. Okay, and then temperature change, big one minus the small one. Okay, so it's gone down by 4. I almost messed up there. Give both values to the nearest 0.1. Okay, so it wants us to record it to the nearest 0.1. Do not just write 4. Do not just write 4. That is not to the nearest 0.1. 4.0 is to the nearest 0.1. They're trying to mess with you there because they've chosen that value to try and catch people out. Meanies. Okay, the student repeats the experiment again using 50 cm cubed of water and finds that the temperature change is that. So this is a show working out Q. Let's go do it. I do remind you to try these questions on your own before you listen to my explanation. Okay, so we're trying to work out Q. Q equals mc delta D. That's the equation you need to memorize. M is the mass of the water. Okay, 50 cm cubed is 50 grams because 1 cm cubed equals 1 gram of water. So 50 m times c, 4.2, that's they're given there, times delta T. Is that what we... temperature change there, 3.9. Okay, calculate. 50 times 4.2 times 3.9 equals 819 joules. This always comes out in joules. Q is always in joules. So it shows about 800. Obviously, you must show you're working. If you just write 800, you won't get a mark. The student uses 2.8 grams. Calculate enthalpy change. How do we work out enthalpy? Okay, let's do it. Actually, we need that other working. Student uses 2.8 grams of nitrate in the experiment. Calculate enthalpy change, delta H. Please sign your answer. Okay. So we've got to take our answer to this one and use it in this one. So we worked out Q. We know that Q is 819 joules. And we want to work out delta H in kilojoules. So step 1, let's convert that to kilojoules. So 819 joules is 0.819 kilojoules. So just go 819, divide by 1,000 to convert, 0.819 kilojoules. That'd be worth 1 mark. You could actually do that later. You don't have to convert it now, but I would generally convert it now. New equation, we want to work out delta H. Delta H equals Q in kilojoules divided by moles. Okay, we know Q, 0.0819. So we need to work out moles. Moles, well, they've given us mass. So moles equals mass over mR equals 2.8. They've nicely given us the mR, 80 over 80. Calculator, 2.8 over 80. Oops. 2.8 was 2.8, wasn't it? 2.8 divided by 80. Correct. 0.0. Careful with those zeros. Very easy to lose one. That's a 0 there. Moles. That's worth. That'll be worth mark 2. Let's go 2. Plop it over here. Mark 3 will probably be for this equation. So even if you can't work out the rest, if you can just write the equation, then you probably get that mark. 0.035. Plug in your calculator. So 0.0819 divided by answer. So assuming no calculator errors, that's 2.34, and then the units will be kg, kilojoules per mole. That's me writing the same as them, so per mole. Check the answer, check we haven't made a mistake. Good. Oh yeah, oh, I forgot something big. Stupid me. It says include a sign in your answer. So the way that energetics works, and it even told us, but even if it hadn't told us, they theoretically could have given us this question, not said include a sign. You still have to. The sign in calorimetry, the sign, positive or negative, is not worked out mathematically. So this would never come out. This always comes out positive. What you have to do is you have to look at the question. Where's the question? And you look at the temperature. Did the temperature go up or down? I think it tells us initially how the temperature went down. So if the temperature goes down, it must be endothermic, and therefore this is a positive sign. If the temperature went up, it would be exothermic, and that should be a negative sign. So you work it out based on whether the temperature went up, negative, temperature goes down, positive. Okay, moving on. Describe the test to show that ammonium nitrate solution contains ammonium ions. So test for ammonium ions, 3 marks. Okay, oops. There's a bit involved, this one. Again, just memory though. Just got to remember this. Okay, so step 1. Add sodium hydroxide to solution. Water do nothing. Step 2. Heat gently and hold damp red litmus paper over. Gas evolved. So a gas will start coming off. But this gas is ammonia. 3. Red litmus paper will turn blue. You could also use universal indicator, which would be yellow to blue. It's fine. I'm sure that's the marks. Let's just see where the marks are. So sodium hydroxide for 1 mark. Test the gas with damp red for 1 mark, or universal color change for 1 mark. Yeah. Okay. E. In another experiment, the student adds anhydrous copper sulfate to distilled water. Explain what the results show about the type of reaction. Slow down. In another experiment, the student adds anhydrous, so we're adding anhydrous copper sulfate to distilled water. The table shows the results. Okay, so temperature's gone up, exothermic. Explain what the results show about the type of energy change that occurs when anhydrous dissolves in water. Easy. So this is simply saying, let's pull this over here. Because the temperature increased, the action, or the, let's use that language, the energy change must be exothermic. And the reaction, let's explain what exothermic means. The reaction must be releasing heat energy. That's the mask. Temperature increases, the reaction is exothermic. Oh, 1 mark, you didn't even need to say about releasing heat energy. And that is it. Okay, awesome. Hopefully that was helpful. If I can face it, no, I'll probably will do paper 2 as well at some point.